Yeah.
All right. Good morning, everyone. So today I'm very excited to be presenting to you your final project assignment, and we're really going to focus a lot on talking about that. Because I think there's going to be some different moving parts. I want to make sure everyone understands. And then afterwards, we're going to set up the team. So it's going to be a two-person team to conduct this, but I will mix you up. So you're probably not going to team up with whoever you're just sitting right next to you, just as a heads up. All right. So I just pushed to GitHub the final project instructions. I want to show them on my side, but they're already up there. And we set up, I set up here, I think what's going to be a really cool exercise for you to work with. So let me navigate that on my side. Oops. Okay. All right, so there's a folder called 06 Final Project that once you pull that folder, you're gonna see there are two subfolders in there. One is if you want to do your final project based on a experimental design analysis, you would follow the first instructions. If you want to do the machine learning final project, we go on the second folder, 02ML. And just to clarify, you choose one, right? Whichever one you would like to further expand the skills you develop in this course. Both of them have challenges in different ways. So maybe at least here in Athens that I can see you all, can you just raise your hand if you're planning to do the design analysis? Okay, so 3 people here, 4.
Does that mean we can no longer use our own data if we're in a group of two?
So you mean like if you do the 02ML?
Oh, no, I mean, for the O1 design.
Yeah, so for the zero on design, the goal is that you will use your data. That is the goal of that
Okay,
exercise.
if we have two people in a group, we have to choose.
Oh, yeah, so in that case specifically, so if you're working like I would probably pair you up with somebody that is interested in design but does not have their own data so they can learn from you and then you can help each other. If we can make that combination. If not, then the experimental design specifically I would allow for solo, if that is the case. Yeah. All right, so let's walk through. So again, you choose one of these routes and you do just that one. Let's talk about the 01 design here. So if you just launch that. So basically, regardless if you work in doubles or alone, you will be asked to do all this through GitHub and to have everything you produce fully reproducible, keeping track with staging, committing, pushing. And if you work in doubles, I will check your commit history to make sure that each person is working, a similar amount of effort. So let's say if a person that does not have experimental data but would like to explore that analysis with someone else, it would make sense that the person that owns the data does a lot of the work because they know the data and so on. At the same time, I want you both to work together so the other person that does not own the data but is part of the team can also contribute either with code or maybe writing and so on. So regardless if you're doing design or machine learning, you will be asked to work collaboratively on GitHub. And I will check to make sure that both people, if you're working in doubles, that both people are working a similar level of effort. So I just have some instructions on how I want you to set up. And I'm not going to go through that in much detail, but you can read this on your own. Basically, just like we did in class, the person that owns the data goes and creates that GitHub repo starting on GitHub and then do a clone on their computer. They invites their collaborator to collaborate on GitHub. That person then clones on their computer, and then both people have push rights to that repo. So then you just coordinate like, hey, work on this part of the code. I'm going to work on this part of the code, and you work together. Both from each one of you from your machine, but having GitHub as a centralized point of your project. So the design analysis is going to look kind of like a paper, and you can even though, I think you can use this to basically set things up as you would write the paper of the data that you're analyzing. So I want to, a short, or not a short, but a 3-4 paragraphs introduction. So I understand what is the issue you're trying to solve with your analysis. Again, this is your data. I'm not giving you data. It's coming from you. So you need to explain to me as a reader of your paper in the future what you're doing. You need to clearly have hypotheses and objectives. These need to be testable. You need to be very clear on what is your hypothesis and your objectives and how they're connected. I wanted to tell me your material methods in a way that I can make sense of what you did, how things worked, what are your treatment factors, what are the levels, what is experimental design, all those things that we went into class when we talked about the experimental design side of things. If you're doing something more complex, like let's say if you're doing a repeated measure, I want you to explain to me exactly how you're doing that, what matrices you tried, what metric you use to select the best model, and so on. So everything, all the workflows we did in class, I want you to be able to explain to me that here, so your study design, here's more specifically where you would explain your treatment design, experimental design, number of reps, how things are related, how experimental units are related in your study. Then I want you to describe to me your statistical analysis, what you did. So really, when I'm reading papers, I don't know if you've had this experience, but you can really tell when you're reading papers if the person really knows what they're doing by how much they're reporting on their statistical analysis paragraph. If they just say ANOVA was performed with Tukey test, maybe they know more than that, but they are really not descriptive enough. I really like people when papers say, well, I used package L or function LMER from package LME4, and my response variable was X or was whatever name. My explanatory variables were this, and that, and this was treated as fixed, this was treated as random. That person describing something to the extent that if they just give me their data, I can rerun the whole analysis without asking them any questions, right? Because I really know exactly how they treated their model, while function, fixed random, and so on. That's what I'm expecting of you. I want you to fully explain to me in a way that is reproducible, that if you were to give me this in your data, I would be able to rerun everything, even if you don't give me the code, just because you were so explicit in how you analyze your data. Then, of course, you want to do your results here. So here, there's going to be a lot of coding. So here's where we basically, on this script, on the design project, you will provide me this script, this Quarto file with your code, with your data, with everything that as we did in class, which is going to be different from the machine learning one. We'll get there when we get it there. But so basically here, I want you to develop like your EDA, your wrangling, whatever you have to do to create your plots, to create your results, running your model, checking assumptions, all those things that we did in class, I'm expecting for you to show here. And I also want you to be like interpreting your outputs, right? So I do want you to, if you just show me an output and don't interpret it, you just lost half the points of that part. So really make sure that you interpret what you're seeing, that you tell me. It's kind of like the results section of a paper, right? So you first start talking about maybe the range of values you found, then you see what was significantly what was statistically different or affecting your model, and then you talk about mean comparisons and so on. You don't need to discuss your results as far as I want you to come here and discuss with the literature, so that part is not going to be required. It's more on the analytical side of things. And then here just have some tips of teamwork on GitHub. So one thing that as you're working with another person, maybe for the first time on GitHub, you're going to realize that you may run into merge conflicts, which is basically when two people are working on the same file, on the same part of that file separately. So the first one pushes and then it goes through. But when the second one pushes, it's going to say, oh, the file that you're pushing has already changed. And GitHub does not know, or Git does not know how to reconcile that by itself. So you have a merge conflict. It's something that can be solved but I would try to avoid having merge conflicts. So I have some tips here as far as how you can avoid that. So one of them is so you make changes before you push, you first do a pull. So if your classmate has already changed that file, you're gonna get that change first before you push. Also something I've used in the past, even if I'm just working by myself, but especially if I work in collaboration with others, is I use my issues tab of a GitHub repo as a to-do list. Because you can say what, like, like next steps would be, I don't know, to run EDA or to run the ANOVA, to get the means. You can list those things and you can assign people to those tasks on each one of the issues. And then when you're done, you just close the issue. So it's kind of like a cool to-do list as well. You can assign that to people and it's right there within your GitHub repo. So to submit your work, if you're doing the design part of the project, you basically render this file here, and you're going to, I have some notes here of how to make your final render version professional. So remember, this is your final report. It needs to look professional, right? Imagine as if you were submitting this to a journal or maybe to a future employer. You want this to look sharp, to look professional. So I have some tips here of things that you can do to ensure that happens. And then you basically submit this by April 30th on ELC by 11:59 p.m. So this is the file you'll submit, the project instructions. So if you just go through these instructions in more detail, you're gonna, have a better idea. I just did a quick run through of what I'm expecting of you, but as you read through this, you're gonna have a better idea of what to do. Yes.
So in terms of this, statistical analysis part, how thorough do you want us to be on explaining everything? Do you want like line by line, please use this package for use clean names for data wrangling to get our data in like how thorough do you want us to be, like step by step everything we did, or kind of?
So normally the wrangling side is not something that people really describe. It's going to be more of like so normally I think of like what I like to see in the statistical analysis description is like what function from my package, what was a response variable, what were your explanatory variables, and on the explanatory variable side, what was random, what was fixed, and so on.
Okay. And then in terms of like when we're setting up the introduction, we don't need to include citations or anything, unless we really want to, I guess.
Yeah, I mean, you don't have to include citations we didn't cover that in this class, but well, just as an example, some people write papers completely out of Markdown, which Quarto is one type of Markdown. So there is functionality to adding citations within a Quarto file. If you want to go that way and learn how to do that, you're welcome to, and include your citations, because it really works like any other citation software. It actually uses on the backbone it uses. So I use Zotero on my computer. So there's a way that you basically connect your Zotero library with RStudio, and it sees all of your citations, just like if you're working on Word and entering citations. So if you want to do that, you're welcome to. You don't have to, but I think it's a nice skill to learn as well if you want to explore. All right. I guess before we move to the machine learning one, any questions about the design one?
Roberto, can we create like another script to do all the wrangling steps and then just put all the outputs in this file, or are we expected to do everything just in this file?
So for the design kind of project, you are expected to show me the code as well.
Everything in here.
Yeah. So
Okay.
I would recommend you do all on this file.
Okay, thank you.
All right. Any other questions before we move to the machine learning one? All right, I don't hear any, so I'm going to close here. As you notice, I'm not giving you any data set because, again, this is your data set that you're going to be providing here. So that's why you don't have any data there. All right, so going to the machine learning final project. If you open that, I have some more files for you. let me just launch the instructions first, and then I'll tell you what files I'm providing you as we go through the instructions. All right, so the initial part of the instructions are just the setup of your GitHub repo. That applies the same way as we just talked about on the experimental design final project. So you're still gonna, if you're working with another person, and if you work alone, doesn't matter, but that you're still expected to do this through GitHub to follow all of our reproducible practices as far as organizing files in the proper way, naming things appropriately, adding, making sure even your code files have a name that makes sense, that follows a sequence, right? So normally, like, let's say in this case here, you may have more than one script. You most likely have more than one script. Make sure you name those scripts at like 01, something 02, something else, 03, something else. So you follow the order on your files as the same order as you're working through this project. And again, all the setup on GitHub with two people working together applies the same. Okay, so let's talk a little bit more about this because it's going to be a completely different set of data. It's going to have different challenges, and it's just going to be a different way than the design overall. So I'm providing you with a corn variety trial data set. We did not see this data set in class, so it's a new data set for you. This is basically a data set that has over 664,000 rows of data that span 10 years from 2014 to 2023. 45 sites in the US. I don't know exactly the number of states, but it's a good number of states here. So 45 sites. Of those 45 sites, 2 of them were here in Georgia. And we have a total of 270 site years, which is just the combination of a given site with a given year. Where each one of these trials, we're evaluating a lot of different corn hybrids. So we have a total of 5,000 different corn hybrids in this data set. So this is another dimension that you have not seen in our example with the cotton variety trial. What am I giving you? I'm giving you the training data. Well, I'm giving you training and testing data, and I'll talk a little bit more about what I mean by that. But I'm giving you the training data for the years 2014 through 2023. That includes trait. So three CSV files, as we're going to see here. You have a trait information CSV file that is going to include site, year, hybrid name, the yield. So this is corn yield in megagrams per hectare, and the grain moisture. I just want to make a point here that the yield that you see on this trait information is at whatever moisture it is being reported right next to it. You will need to transform this to a 15.5% moisture, which is the default that we report corn grain yield data, just as a heads up. You're going to have a meta CSV that includes site, year, previous crop. I guess didn't include here, but includes planting date, harvest date, and then longitude and latitude. So this gives you some more information. And then on all those trials, or at least most of them, you're going to have soil information. So there's a soil information file that includes site, year, soil pH, soil organic matter, soil phosphorus, and soil potassium. Now, these soil data are actually sampled and sent to a lab, analyzed results, soil data type. It's not something you get from open source. However, you can also retrieve from open source if you wish. So there's going to be a lot more room for you to play around on the machine learning track of the final project. But let me just show you here the training data, just so you get an idea of what I mean. So the training data, I'm giving you the training meta, or let me begin by the training trait. That's the first one. So training trait, it has over 150,000 rows. We have, let me zoom in a little bit. You have year, site, replicate block, the hybrid name, they planted, they harvested, yield in megagrams per hectare, and grain moisture. This is what your trait data has. If we go on the meta, training meta, you have year and site, previous crop, longitude and latitude. And on your training soil, you have ear, site, soil pH, organic matter, soil potassium, and soil phosphorus. This is what you are receiving. So you're going to basically use this training data as if were your entire data set. So in class, we started with the whole data set and we split that in training and testing, right? Here, what we had in class as our entire data set is what I am giving you as your training data. The reason for that is because in class, we had our full data set, we split in training and testing, but you knew what was the value that we were trying to predict on the testing. We had that value, right? We had a value for cotton fiber strength on the testing. In this case, I'm giving you test data that is very similar to the training data I'm giving you. However, on the test data I am giving you, you do not have yield. So on the test set I'm giving you, it's going to be for a whole new year. So it's for 2024. This year is not part of our training set. So you're basically looking at all data available for 10 years, creating a machine learning model to then predict the yield outcome of the following year. That's kind of the idea here. So on the training set that I am giving you is for a whole new year, 2024. And here are the files that we have for the test sets. I still give you, so the meta information is very similar. So we have here for 2024, we just have 25 sites in just 1 year. So basically we have year, site, previous crop, longitude and latitude again for your meta. For the soil, you have the same information, year, site, soil pH, organic matter, soil potassium and phosphorus. Now, what on the training I call training trait is what you are going to be submitting, which is the testing submission. So what is this? This is basically the year, the site, the hybrid, and then yield is empty. That is by design. It's because I want you to give me this column here, yield micrograms per hectare, is what your model is predicting for those sites, years, and hybrids to be. So this is one of the things you'll submit to me is your predictions for the yield of this hybrid on this site, on this year, on this data frame here. You're going to complete these values based on your model predictions. So notice you do not have what I'm calling testing. You do not know the yield of that data. You are making a prediction of that. And only I on my side have those values. So when each group that's doing machine learning approach sends me this file, I'm going to combine this with my actual observed yield and then do our square MSE and see whoever got the best model. That's how it's going to work. Now, one point here is, this is going to be also part of a competition. It does not matter how good or bad a prediction you make, how good your model is not going to really impact your grade, right? So it's just part of that competition of, let's say, who was able to create the best model to predict a whole new year of unseen data. So it's just a little fun, little competition or a final project. Your model could completely do a horrible job here. You can still get 100 points, right? So the quality of the quality of the predictions of your model are not going to impact your grade. Of course, what impacts your grade is that you, at least on your side, show me you did the best possible to train the model. So you did all the steps that we went in class when you train your model. So this file, the testing submission is one of the things you'll submit to me. It's basically, you're just going to fill in all these NAs for yield with your predicted value from the model you trained based on all the previous year's data. Let me close this. So I'm giving you all the same predictor variables to begin with, and then you just have to give me the prediction of the yield that I'm not giving you on the testing. So your goal here is to basically train machine learning models using the training data I'm giving you to predict yield on the test data that I'm also giving you. But again, you should treat the training data I'm giving you as your full data set Because then you split that training into training and testing and do everything we did in class. Because you still want to have an idea from your side, from the data that you do have, of how well your model is doing, right? So you still need to have your own test set, which is going to be different from the one I'm giving. So one difference from class is you are not provided with the test data yields, which is the predictive variable, only with the predictor variables of soil, coordinates, geospatial coordinates, and so on. Therefore, using the training data wisely to create a predictive model will be important on your side. Okay, a few notes here about the machine learning part. This is going to be completely up to you. There's a lot of steps that is going to be completely up to you that you don't have to follow exactly what we did in class. So one of the things is notice that on the machine learning track, I am providing you with longitude and latitude. I'm providing you with some data like soils data, previous crop, planted harvest date. I'm not providing you with weather data, for example. You have it, if you want, you don't have to, but if you want to try to get the best model, you may want to incorporate open source weather data here, like we did in class. Or maybe other types of open source data that we did not have a chance to go through in class, but that exist. So if you think of anything else, you can pull here as an open source data to add to your data to predict, to create the predictive models, you're welcome to do that. And you're encouraged to leverage open source data, especially because the reason why I chose, or one of the reasons why I chose this data set is because it has longitude and latitude, which allows you to pull all sorts of open source data based on geospatial location. So again, this is going to be up to each team. If you want to pull other sources like weather or maybe others, you're welcome to. If you don't want, you don't have to. It's probably just your model may not be among the top performing ones. And this is really an example that I think it's like once you go through this entire exercise, I think it's going to be really interesting because you're going to start realizing that, of course, in class, I have to give you some structure for us to follow through. But when it comes to like real life examples, like this is a real life example, it's really going to be up to you to decide what data you use, what features you create out of that data, what models you train, how you train the models. All those things are up to you. All right, so a note on feature engineering. Again, this is going to be up to each team, what you want to do with the data that you have. But really the goal is to create variables that you think would connect better with your predicted variable. So for example, in class, we pull weather data and we summarize on a monthly basis. We could have summarized in many different ways, using different windows, using different summarizing functions, and so on. So this, again, is going to be up to each one of you. How do you want to do that feature engineering if you do bring weather data, or maybe even other data that I'm not talking about here, but you could bring? So perhaps if you do bring weather data, you may decide to summarize that in a different window size, maybe the whole growing season, maybe every 2 weeks. Maybe you create crop growth stages and then use those as the summarized windows. So there's a lot of different ways that you can think about the feature engineering side. All right, so we talked about data retrieval, external data retrieval with open source data. We talked about modeling or feature engineering. Now talking about modeling strategies. So here's how this is going to be set up. Every single team is going to be asked to run 2 machine learning models. One is going to be XGBoost. Everyone's going to run XGBoost. There's still going to be some variability because maybe one group brings weather data and summarizes by month, or other group brings weather data and summarizes by, I don't know, crop stages or whatever it is. So there will be variability even though you are all going to be running the similar model, which is XGBoost. But then besides XGBoost, which everyone's going to be running, each team is going to be allowed to choose one more model type. And this could be any model that you wish. I left you here a list of models that are supported by Parsnip, which is the package in Tidy Models that helps us to do the model specification on the training workflow. So you're welcome to explore that and choose whatever model you want to test. Now, the reason why I included XGBoost as the required one, you have not learned that yet, you're going to learn that on Thursday, is because, well, So Amrinder is going to be teaching XGBoost, and we already saw the results, and we know XGBoost is the best model for the cotton data, at least. It doesn't have to be that way. Maybe other data sets, a different model is going to be good. But just so you have some background here, I don't know if you've heard of this website called, I don't know if it's Kaggle or Kaggle, but it's like a data science hackathon type of website where there's a lot of competitions and people enroll, and I mean, if you get the best predictions, you actually get a monetary award. So it's a pretty cool like hackathon type of website. I was checking some stats on Kaggle hackathons, and basically XGBoost, before we go into deep learning, which we're not going to this class, at least not, I'm not teaching you deep learning in this class. We're still staying within the realm of, somewhat not big data, even though we have like, sometimes here like almost 500,000 rows, that's still not big data. So we're still within big data, or still within, I guess, small data and using tabular data. It's still before making the jump to deep learning. So these models like Random Forest, XGBoost, ElasticNet, Support Vector Machine, all these things are very popular in machine learning. Of all those models on Kaggle, the one model that's the most prevalent on the winners across a lot of hackathons is XGBoost. So XGBoost is one of the best performing models when you still have tabular data before you go into video, image, and things that benefit from deep learning models. So that's why that's going to be the baseline for everyone to do XGBoost. And then again, you can play around and select any other model from the options that we have on Tidy Models, which is on this website here. If you just come here, there's going to be a list of, I don't even know how many models there are here, but there are many models. Like there's 6 pages here. Yeah, so 146 different models you can choose from. Of course, some of them are going to be only applicable to categorical response variables, which ours is numerical, right? So yield is numerical, is not categorical. So some of these models are going to be just for categorical, but there's still a really good number of models that you all can play with and choose from. All right, so you have a choice here of what open source data you bring, how you do feature engineering, what is the second model that you train. And
Dr. Bastos,
yes.
I have a question like that extra model, like the model of our choice, maybe like either should be this random forest or this conditional CIT or this kind of like this model that are taught on the class, or we can choose any other models like support vector machine, anything.
It could be one of the ones in class. It could be a new model. I think that actually, so it could be either. I think this gives you a chance to learn a model that we did not learn in class. As you saw in class, we just covered 4 or 5 models, and there's like 146 available just in Parsnip. There's no way we would cover all of them. So I think it would be a good option if you want to choose a different model, so you can learn about, so every time you learn a new model, you need to understand how it works, what hyperparameter values it has, how can you train it, what type of variable importance can you extract from it, what interpretability you can get from it. So if you want to try a completely different model, that's welcome. And I think it helps on your learning as well.
Okay, thank you.
All right, so the other place where we're going to have a lot of flexibility is on the training strategy. So for both XGBoost and the second model that you choose, the entire training process is up to you. As long as you follow the overall idea and this overall steps, the details of each step is going to be up to you. So for example, you're going to have a choice of how you want to do your split. Maybe you do a 60-40, maybe do a 90-10. It's going to be completely up to you. What pre-processing steps are required? I would recommend you take a look at the specific pre-processing steps of the models you choose, but this is going to be up to you to choose what are the hyperparameters available and whether or not you train all of them. And if you don't train all of them, which ones you train, completely up to you. What is your search strategy? We talked about a fixed grid. We talked about iterative search. You may get to a different answer depending which one you use, completely up to you. What resampling strategy you want to do? We saw in class doing a V-simple or V-fold resampling strategy where our V was 10. You can do that strategy. You can use 5, 10, 20 folds, or maybe you can use a different resampling strategy. Maybe you do a leave one out, which we did not see in class, but it would be another one. Then which metric you use to select the model? Maybe you use R-squared, maybe you use RMSE, maybe you use something else, up to you. And then which type of model selection to use. You saw in class, we explored selecting the best model based on a given metric, selecting the best within 1 standard deviation or standard error, selecting the best within a given percent loss. All that is completely up to you. You decide what you want to do. And then finally, which I think is going to be really cool, and I think I'm going to really push you here, is the final part of this is how you communicate your results. So the way that you're going to turn in your results on the machine learning side are different from the way to turn in on the design side. On the machine learning side, you will be asked to create a Shiny app. We're gonna have one lecture on Shiny apps as well. So I'm not just like throwing this at you completely blindly. So we're gonna have a lecture coming up that you're gonna see what is a Shiny app, how we create a Shiny app. But really, the cherry on top of your machine learning is to communicate your science, communicate your results in a very interactive way using Shiny apps. Here in Athens, I can see a little bit more easily. Can you raise your hand if you're aware of a Shiny app is? Okay, so not a lot, just one, just shake. So let me just show you very quickly here. What is a Shiny app? Well, I'm going to show you one of the ones that we created. Let me see. All right, so I just want to show a quick example here of a Shiny app that we created in my team. We created a few of them already, but while this is loading, I just want to explain to you what you're going to see. So we used cotton variety trial data in Georgia to basically create a Shiny app that let's say if you're a farmer in a given county and you want to know what is the best cotton variety for your county or your field, we basically created an interactive Shiny app for that. So this is already live, like anyone can access. So here, I mean, we have many tabs here, but basically this is an interactive map showing where the trials were conducted. So number of trials in each one of these counties. This is just the initial page. Can come on the variety selector. So here you would basically choose if you want to, let's say by county, and let's say I am in Tift County, or let's put Scriven County, irrigated cotton, and I want to look into lint yield. So this is a cotton. There is an analysis that we did for Finley-Wilkinson analysis, which you don't have to know much more about that, and then gives a ranking of the varieties here, which this ranking of the varieties changes depending on the environment you select. Then we have environmental characterization, showing a list of all the trials in the data set and where your trial compares with all the others. It has a variety characterization, so showing data for each variety on that county specifically on each one of the years that we have data for that, so we can see what are the varieties and if they're yielding more or less than the median. There's weather information here, so the orange line is whatever county you select compared to the rest of the data set, and then a full list of the experiments that a person can check. So this is a very, very complex Shiny app. I don't expect you to do something as complex as this, but I do expect you to do something that is interactive and that you can show someone the results of what you're doing. So maybe let me show you a little simpler one also from my lab. Yeah, so this is the initial beta version of the one I just showed you, which perhaps is more aligned with what I would expect of you. Let's just wait for it to load. So here, basically, we have the same data, but just for 1 year. We're not providing a full variety recommendation, but we're showing the data interactively. So I can choose which variable I want to see. So lint yield, color. So all of these other variables are cotton quality variables. If you change the variable you select, the map changes, and this also changes. So here you just see the value that you select here. So let's say I want to do yield again. That's the most important. You just get an interactive map showing how the yield ranged. So this is like a zoom in, zoom out interactive map. I have the trials ranked from lowest to highest here. So we can see like what was the lowest yield in that year, what is the highest, and how it compares to all the mean of all sites. And then here is just a quick summary of precipitation and maximum temperature over the growing season, where each line is a trial. So perhaps this is something more similar to what I would expect of you, is like to show some graphs and at least one of them to be interactive. There's a whole new Shiny app gallery in RStudio or POSIT website that you can check and get some ideas, get the code from there, really get some nice ideas of what you can do and how you would do it. So if we just, if we just type Shiny app gallery, there's a lot of really great examples of some very simple things, some more complex things, but you can explore that to really get an idea of what people are doing and what is possible for you to do as well. For this final project, let me come back here. What I want you to do is, after you did all of your training and you compare your XGBoost model with the other model that you selected, maybe you choose one of those, so you don't have to show results of both models, just one of them. And I want you to bring some of that into your Shiny app. So while the Shiny app design is completely up to you, it should contain these minimum requirements. It should have at least one EDA, so exploratory data analysis plot on yield based on your training data. Maybe this is a geom density. Maybe this is a map of the US with the points. Whatever it is up to you, but it needs to have one EDA based on the yield, which is our predicted variable. You should have at least one EDA plot on each predictor types. What I mean by predictor types or predictor groups. So if you have soil data, the one I'm giving you, you have, I think, 5 variables. I want you to show at least EDA on one of those variables. And then if you bring weather data, the same thing. I wanted to show me at least one EDA plot on one of the weather variables. Of what you show me, at least one of them needs to be interactive in the sense that either the person can zoom in, zoom out, or maybe they can select what variable they want to see on the plot. So there should be some interactivity on your Shiny app. And then you need to show me some results of the best model that you were able to train. So I want to see a plot showing the most important variables in your model, whichever model it was. And then a plot of the predicted but observed with R-squared and RMSE on your testing set, not mine. Remember, I'm giving you a training set that for you, that training set is the whole set. You're going to further split that into training and testing. And then once you do all your training, decide on your final model, then you make predictions on my test, which you don't have the actual observed values. That's the idea. So I do want to show me here predicted by observed plot with fit metrics based on your testing set. And that's pretty much it. So then I have here some troubleshooting notes. Please go through those. I'm not gonna really read this to you in class, but please make sure you go through all that. And then to turn in, if you do choose the machine learning side, you will turn in different things than the design side. So here, what I want from you is the URL of your GitHub where you developed all this analysis. So you're not going to send me a Quarto or an HTML file. That's not what I want from you. I want the URL of your GitHub that you work collaboratively to create all the results that you are doing here. I will be watching for things to make sure you're following reproducibility standards, right? So I want you, just because it's not, so imagine that all the process that we learn in class of having different scripts, having heading levels, having comments, making things very easy to follow, that's what I'm expecting of you. That's what I'll be checking on your GitHub as well. Then the file you're gonna send me is the testing submission CSV. So the one I showed you earlier, where on the testing submission, you have site, year, and hybrid, and then the EO column is empty. You wanna send that to me, but of course, you need to have your EO values filled in based on the model that you train. I'll be right there with you, Shakir, just give me a sec. And then the third thing you're gonna submit is the URL for your Shiny app. As long as you submit these three things, so two URLs, one for a GitHub repo for the results, the file with the prediction that you're making, and the URL for the Shiny app, that's what I need from you. You're gonna submit all that on ELC as well by the same deadline of April 30th. Now the grading here, well, before I talk about grading, Shakir, do you have a question?
Yeah, thank you, Dr. Bestus. So in the class, you mentioned that from machine learning workflow, we should always expect to see the predicted versus like X versus Y plot and the variable importance plot. So since I did not see anything in your instructions about the variable importance plot, are we supposed to make that or can we skip that?
So you're gonna show that on your Shiny app. Yeah, so on your Shiny app, if you go through, so I just, maybe you didn't get that part, but on your Shiny app, I want to see your most important variable from whichever model you select to show on the Shiny app, and then a plot of the predicted by observed as well. So those two components you will show on your Shiny app.
Okay, thank you.
Yeah, thanks, Ricky. All right, and then, so the grading here is gonna be a little bit different, right? So I don't have like specific questions that you're answering that I can really see question, see answer, give you a grade. So how am I grading your machine learning exercise? You will be graded based on if you follow general workflows that we did in class for all steps. So if you pull open source data, you need to have a script for that. It needs to be very clear what you're doing. It needs to be everything in the code. If you do feature engineering the same way, like I need to be able to look at your code and understand what you're doing, which most of the time just the code is sufficient. But in your case, I do want you to explain to me, even if it's just a sentence, like in the chunk below, we'll pull data from this open source database or whatever it is. And then follow the machine learning model training techniques of data split, hyperparameter fine tuning, doing the search, choosing the best model, creating your interpretation plots of, the variable importance, predicted by observed, and so on. So if you just take the script that we did in class and you follow similar workflow, you should be good. I will be checking in this. So point number one, I will be checking on your GitHub repo. So I'll be going there, taking a skimming at it. If I can easily understand what you're doing great. If I cannot make sense of what you're doing because your code has no subheadings, has no headings, is everything messy, then you lose points here. I want you to follow reproducible standards like using sensible folder names, file naming, script organization, script comments, and all those things that we have been doing in class. So you know what level I'm expecting of you is the same as what we're doing in class. You are expected to collaborate with your partner on GitHub. So this is going to be important. If I check your commit history and just one person has committed like 90% of the time, then the other person is going to get hurt on their grade. So make sure that you try to work about, or at least work on the code about similar level of efforts between both of you. Of course, you have to submit all the three pieces that I'm asking of you. So you have to submit two URLs, one for your GitHub repo, one for the Shiny app, and then one file with your predictions. Of course, you need to submit on time. If you submit later, you lose points for that. And then your Shiny app dashboard has to have the minimum requirements that I listed above of having, well, I'm not going to reread it. They're right here. Or not right here, I guess, but somewhere in the script. And then if you choose the machine learning track, there's a little bit extra, right? Because you're all if you're doing this track, you are competing with your other groups. And so the way that I'm going to have in the end a ranking of whoever was able to create the best predictions. And so whoever gets whichever team gets to create the best predictions on my test set, which you do not have. Again, you do not know the observed yield that I have on my test set, you don't have. So you have to make sure that on your side, you do the best possible to train a model that's generalizable, because you're going to be predicting on data you have not seen. So whoever, once you all submit your predictions, I have a column with the observed value. I'm going to check my observed value with all of your predictions, see whoever got the highest R square, and that team is going to receive an award and also bragging rights on this hackathon. All right, that is everything about the machine learning track. Questions?
Dr. Bastos,
Yes.
but this one, does it have to be like a team or we can do it alone?
This one is going to have to be in doubles. Yeah. And we're going to talk about that in a second here. So we're going to take some time in class to set up the team or the interest in the teams as well. But I will first, before we go there, I just want to make sure or check if you all have any questions. So one thing, a word of caution here, especially on the machine learning side. I do expect that the training part of this is going to be the fastest part of it, the one that you're going to spend the least time. I do anticipate you spending a lot of time on wrangling. You're going to have data sets that have different dimensions, as you're going to see. So you're going to have to think through how to solve that. If you're going to be pulling open source data, that's going to take some time. If you're going to be doing feature engineering, especially if you want to do something different from what we did in class, that's going to take some time. The training is going to be the fastest in my opinion. And then the Shiny app development is going to take some time. And at least it's pretty quick. Like it's pretty quick to do a Shiny app. I can do like if you go on Copilot or ChatGPT and you ask, do a Shiny app, show me our code for a Shiny app in R that does this, and that. It gives you code, you copy paste into R, you run, you have a Shiny app. It's pretty simple. But you're going to have to think more about it, right? You're going to have to think what are you going to show, how are you going to show, what are the components of your Shiny app that you'll be implementing. So it's going to take you some time to do that. So I would say probably the actual training part of the machine learning exercise is the one that's going to take the least time. Everything that comes before and after will take more time. Do not leave this to the last minute, because this will take you time. And I'm sure some days you're going to hope that you just have one more night, you could just sleep and wake up fresh to take another look. Give yourself those nights and that time for you to do that. All right, so I think that's all I had before we create the teams, but I will stop the recording before we do that. So I just want to, before I stop the recording, anyone has any questions about either the design track or the machine learning track? Yes, Travis.
So we have to decide today which one we.
Yeah, we're going to decide today because we're going to make the teams today. I want to give you the most time that I can for you to start working on this. And so we're going to set up the teams today. All right. Any other questions before we move on to team making? Okay, I don't hear anything, so I'm gonna.
Dr. Bastos,
Yes, Shakir.
I have a quick inquiry. Are we gonna start on the XGBoost today?
We're gonna start on Thursday.
Okay, thank you.
Yeah. All right, I'm gonna stop recording here and then we'll do the teams.